Hey, hi. Too bad that I cannot be today in your, well, in presence in the classroom. But I really want today, I really want to spend some time with you today and to talk about mass balances. So let's start with the class. Okay, so first things first. So what you're gonna see here, you'll receive a handout. And in this handout, you're gonna be following all the materials of this class. So the first thing is to teach a little bit about the continuity equation. So what is the continuity equation here? So this, we're going to be talking about flow rate. What that means is how much water is passing at a certain period of time. Okay, typically, the continuity equation is expressed as follows. So imagine that we are monitoring an area, let's say the area of a river. And then in this area, we know what is the velocity of the water that is passing through it. So we have an area and we know what is the velocity that is passing through it. So imagine that this velocity vector, we put it on every side of the area that we are monitoring. When we're doing this, as you can see here, now we have a volume of water that was created by the area that we're monitoring and the different vectors that we have for the velocity. In this case, the flow rate is equal to the velocity that passes and the monitoring area that we were talking about. How much water is passing in a unit of time? Let's say how many cubic feet per second are passing at a certain cross-section. It depends on the area of that cross-section and how fast the water is passing through that cross-section. That's what is saying this. This is typically how the continuity equation look like. Okay? Now, what you're going to be seeing is that throughout water resources management, we're also evaluating these flow rates or addressing how much water is passing, how much water is coming in and out and is stored through certain periods of time. So in this case, let's imagine that now we have a control volume, okay? So this control volume is a cube, the cube that you are seeing here. Imagine that we have this cube of okay, now imagine that we're monitoring this cube, and in this cube, what we're going to have is certain amount of water already inside that control volume. So when we are starting our experiment, we have that cube of that control volume, and inside that control volume, there is certain amount of water that is already there. We call it certain initial storage, or SO. Now, we're going to be having certain amount of water that will get into this control volume, and we will have also a certain amount of water that will go out of that control volume. Okay, so how much the storage of water inside this control volume changes? So the change of storage, this delta ST, this change of storage in this control volume it will depend on how much water comes in, so the inflows into the control volume, and how much water it goes out, which are the outflows out of this volume. So as you can see here, the change of storage will be equal how much water will be if it increase or decrease that change of storage. How much water is stored here will depend on how much water moves in and out the control volume. Okay? This, what you are seeing here, is the continuity equation, the mass balance equation that we will be discussing throughout today. So let's go back again to let me show you an example of this change of storage. Okay, so here we have the same exact equation, which is the mass balance equation. Okay, so this is the mass balance equation. Okay, now in this mass balance equation we have the inflows, and in this case this change of storage will be, well, let me step back a little bit here. Okay, let's start with the inflows. Let's say that we start at a certain period T0. So we have certain initial storage, as you're seeing here. Okay, then we're gonna put some water in, and then for a period of time, let's say 1 month or 1 year, we start with an initial storage in a control volume. We can define the control volumes in different ways. I'll explain you how. But we put some water in, and then out of that same control volume, out of that bucket, we take some water out. At the end of that first year, first minute, whatever we're using as the unit of time, the final storage will be how much water we started with that, how much water we started, then how much water we pour in, and how much water we extracted out. That what I'm showing you is for this storage here, at the end of the time number 1, in order to know what was the storage, let me see if I can actually highlight this guy. So for this storage, the storage at the end of this period number 1 will be equal to how do we start the storage, what was the water stored on that control volume in the previous time step, which is this, how much water we pour in, that will be this, what you're seeing here, and how much water we took out on that period of time. Basically what I'm doing here is that showing you that the change of storage in this case, so between the current time step and the previous time step, what if the storage increase or decrease on that period of time, it will depend or is equal to how much water came in and how much water was extracted from that control volume. Okay, so we can actually do the same for different periods of times. So again, as I was telling you, for this at time equal to 1, so let's say we started at the beginning of a month. At the end of the month, in a particular storage that you may want to imagine, let's say a reservoir. So the storage in a reservoir at the end of the month will be, which is here, sorry. So the storage at the end of the month will be the storage of how it started on that month, how much water was coming in into that reservoir, and also how much water was extracted or came out of that reservoir. Okay, this should be actually, this is one. Okay, we can do it for the following time step. So what we can do here is do exactly the same. So let's think about this. For this will be t equal 1, a period of time equals 1, then here we have t equal 2, and this can be a time equal 3. Again, these are units of time. We can say that these are years, and we're going to be counting all of these every years. We can count all of them as months. These can be also decades. This can be also days. But what we're doing here is a simple accounting, a mass balance. So again, for t equal 2, so it will be what was the storage at this initial, at the previous time step, how much water came in, how much water was taken out. That will be this S2, which is basically what you are seeing here, which is the storage at the end of the period of time 2 is S1 plus the inflows to that storage minus the outflows of that at that time step. So as you can see, imagine that you have here kind of a bucket. So you start with a certain storage, and then how much water you put in, how much water you take out at that time step, you record it. And that will be the end of time 1. And then for time 2 is that initial storage plus how much water you're putting in, how much water you're taking out, and then you account it, and that will be this storage at time number 2. Okay? And then for storage at time number 3, so you already have the storage at time number 2 is how much water you're putting in, taken out, and you account for that storage number 3. So as you can see, once you know, so you need to know certain conditions. One of the most important things about the mass balance, and I want you to, this is very important. We use a mass balance to know, to find out all the variables except one. We're always missing one variable that we want to know, that we want to evaluate, to calculate. So using a mass balance equation, we can have all the variables, all the terms already calculated, but one, and a non-variable. And then we use the mass balance to estimate that one. So that's what is going on here. So this is, so if time will be equals to n, the storage at that time n, it will be Sn minus 1 plus the inflows at n minus the outflows at that end point, n time step. Okay? So this is important. Right now, what I explained you here is a very basic concept. Whatever was the volume that we were, whatever is the system that we want to evaluate, we can think of it as a series of buckets and how much water is coming in and out. That's a mass balance approach. Okay, and we're going to be following that bucket, which these buckets are the control volumes that I explained to you here. And then we're going to be counting throughout the time what was the initial storage and water that was coming in and out, and then recording at different time steps. That's the basic principle of mass balance. So let's go to these natural systems. Imagine that for some of us that, for the first group that went last Saturday to the field trip, so imagine that we are in that upper watershed at the Russian River. So in that one, imagine that we have, I don't know, one of those basins that we hike, watershed number 1. And then, so this will be the divide, the ridge, the edge of the basin, okay? And here we have the river flow in this direction downstream. So imagine that what we're now doing there is that we're going to be drawing our control volume. So what will be our control volume? So it will be that control volume. Imagine that we are having an imaginary volume all the way up to the atmosphere, okay? So it's a control volume that is going from the area of the watershed of the basin, all the way up. So what will be our inflows into this so let's say that our inflows into this will be the precipitation, okay? So we're gonna have precipitation as our inflows. And perhaps we may have some water that we want to import into the basin. So here it must say import. Okay. Now, which is here. All right. So these are our two inflows. What about our outflows? In this case, our outflows will be let's say that we have certain evapotranspiration from the plants, and that we are also extracting some water out of the basin. In this case, our outflows will be ET, this water exported, and also how much water is leaving the basin. So as you can see here, all of this is the outflows. All of these terms are the inflows here. So this is I sub T minus O sub T. And that will be equal to the change of storage. That this is actually our mass balance equation that we've been discussing throughout this lecture, okay? That equation is this one here, okay? Now let's talk about, so this is as if we are having our control volumes, and we can draw our control volumes in different shapes. And what I want you to notice here is that once you have defined your control volume, you will be figuring out how much water is coming in and out that control volume, okay? And in this case, the control volume, it was an area, and we projected that area all the way to the top, to the atmosphere. Now this one, imagine that we're gonna be treating the river as a leaky channel or a leaky pipe, okay? So this is our river. So imagine that instead of being in this, sorry, let me explain you this a little bit, this one here. So this is our watershed, okay? The previous analysis can be done from this upper watershed. This analysis here is usually done at the upper watersheds. What about when we're talking, as we're moving downstream in between 2 points where we already know some of the stream flow. So that's what is happening here, or what I try to explain to you here. When you have 2 gauges stations, how can you do the mass balance between 2 stream flow gauges? So the river is running and it's going this way, okay? Within this river, we have a gauge here, and we have another gauge here, okay? Here we have 2 gauges. Out of this river, we may have some water diversions to certain water users, okay? And we will also have certain return flows. Now, we may also, the river may have also some, as I was explaining you that this was a leaky pipe or a leaky channel, it might be losing some water to the aquifers, as we know. And it may be sometimes at certain period of time gaining some water from the aquifers. It may also occur the same. Some of the water might be imported from an outside basin, or it might be that this basin is used to export water to another basin through canals and so on. So let's go back here to our mass balance equation. The change of storage here will be equal to the inflows, how much water is coming in this control volume, and how much water is coming out. So let's start identifying those inflows. In terms of the inflows, we're going to have how much water is coming in from here, from upstream. If there is any water imported, how much of that is there? How much water of the water that has been diverted returns back to the river, and also the gains. There is any contribution from the groundwater there, how much it is. In terms of the outflows, how much water is in this downstream gauge? What is the water exported, and what is the water diverted out of the river? How much of the water in the river is lost to the ground? As you can see in this specific, well, and in this one, as you can see, we have no reservoir, because, and the same like here, if we have no reservoir, then our mass balance equations becomes the inflows, they are equals to the outflows, okay? So, which is basically what is going on here. If the change of storage is 0, then the inflows will be equal to the outflows. That's what is going on here, okay? Now, following the same, all of these inflows, you can actually see that are written here. Now, all of the outflows, you can actually see that they are written here. Now, imagine that in this system, we may know, we have the stream flow gauges. So we do know how much water, we know these variables, this guy here, and this guy here. In terms of water imported and exported, these are usually aqueducts or pipes that we should have some information about how much water is diverted. In terms of water users, we actually know what are the crop that they were using it, so we can estimate it. What was the population? What were the cities that they were using? They were withdrawing water from the rivers. So the diversions, and also what was the discharge, the treatment plan, how much water did they discharge it back. So these diversions and returns is information that we usually know or we can estimate. In this case, the unknown variable are these gains and losses. These are the two variables that we do not know their value. So because of this, what we're doing is just substituting these gains minus losses will be equal to all this Q in minus all this Q out. Okay. If this value is positive, then it will be gains. If the value is negative, then it will be losses. And finally, a surface water reservoir. Okay, so in this case, it's the same. We start exactly from the same equation. And remember that the change of storage, we always can estimate it as the storage at the end of the time step minus the initial storage. That's our change of storage over that period of time. In this case, the inflows into the reservoir are precipitation. It can be precipitation or a stream flow coming in. The outflows of that on a reservoir is actually the water that is released. We call it releases, and so on. And this change of storage is what we were saying, is this a balance between the end of the storage and the initial of the storage. As you can see here, what we're doing here is this OT is actually all of this that we were mentioning before. The inflows here are all these inflows that we mentioned before, and the change of storage. At the end, what we do know, again, remember that we use a lot of, most of the times we use this mass balance equation to find out what is the unknown variable that we want to calculate. In this case, this is our unknown variable, this guy here, okay? So the storage at the end of period, it will be how did it started, all these inflows that we can calculate or estimate a priori, and the outflows that we can be measured or calculated. So basically, that's the explanation of this mass balance. Now, of course, you're gonna tell me like, how does this actually look like? So let me explain you here. How do they look like or how can we calculate it? Because a lot of these equations that we were discussing here, so every time, something that I forgot to mention, but every time that I'm putting a sub t on a variable, it means that it's going to be a variable that it will have a time series data, that it will be changing through time. That's what this means. So basically, if you can, let's start talking for a system, a very simple system here, okay? Imagine that we have a system here that it is a river that is flowing down. And in this river, we know how much water is coming at this gauge. Also, we know we have a demand, a user that wants to divert some water. We're going to have the diversion, and we're going to have how much water is left in the river, considering that some water will be taken here. So again, we're going to be using this mass balance equation, but because there is no storage in this area, so basically, So because there is no storage, there is no reservoir storing the water of the river. So then the change of storage is equal to 0. So whatever water is coming in has to be equal to the water that is going downstream or outside of the river. Okay, so let's start here. So this is, as I was mentioning, this is a mass balance, problem that we were going to be using the mass balance to solve for this system. Now, again, when we're using a mass balance, usually we're using it because there is an unknown variable that we want to estimate. So what are the unknown variables that we have in here? So these are the years and these are the months. So you can see that in year 2015, on all these months, the water coming in is this time series data. Even though I use this as a variable, it is actually associated, it has a time series data associated with it. This demand here is the demand. It's a user that is just requesting some water. And this is its water needs for this specific demand. We have an estimate how much water can actually be diverted and what will be the flow here, okay? So as we know here, our unknown variables are, in this case, this water coming out, this Q out, and also the diversions here. We do know the demands and this, but we are missing the diversions. So in terms of this water out, so how much water will came out of this simplified system it depends on how much water is coming in and how much water is diverted, okay? Now, the problem here is that the water that is diverted, it is, our other unknown variable is this diversion, which the diversion depends on how much water is coming in. Depending on how much water is coming in and what is the demand, we can estimate the diversion. So let's actually, how can we estimate the diversion? So in terms of diversions, how much water we can divert, there can actually be two things that can happen here. So imagine that we're demanding 2 units of water, but the water coming in is 10 units of water on that. So in this case, the demand is less than this Q in. So how much water can be diverted at this point? 2 units. Let me explain it back again here. So there are 10 units of water coming here at this portion of the river. Here, we need 2 units of water. So we have 10 units of water here. And we are, at this portion, we have 10 units of water. And here, this user is requesting 2 units. How much water can be diverted? Well, actually, those 2 units of water, because there is enough water here to provide that amount. Let's talk about here. Let's think about this in April 2015. Now we have 6 units of water available here, and then we have 6 units of water available, demanded or required here. How much water can it be taken? 6 units of water. Now let's take a look at this one here. We have 2 units of water coming in, and the same 6 units of water requested for the user. In this case, even though the user is requesting 6 units of water, it can only be diverted at most 2 units of water. So in this case, what I'm trying to come is with a series of rules. How can we estimate this diversion? In this case, the diversion, so this, it will be equal to the demand if the stream flow coming in is greater than the demand, which is greater or equal as it is happening here. What if the demand is greater than the Q in? Then we will be only able to divert this Q in, which is this second statement. The diversion will be equal to Q in when the Q in is less than the demand. So this is how we can calculate it. We can calculate it manually. So if this is greater than this, then we extract. If the Q in is greater than the diversion, then you extract that much. So if this is greater than this, we can extract this much water. If this is less than this, then we can only extract the water that is coming in. Okay. What about the stream flow? How can we calculate at the end the water that is coming out of this ridge? So in this case, how can we calculate it? So it will be however water is coming in minus the water that is diverted will be the water that will came out of here. So Q out will be Q in minus the diversion at a certain point. So in this case, Q in minus whatever that water was diverted, it will be the water that is coming out. Let me actually go back to this example. So if there are 10 units of water coming in, there are 2 units of water demanded, and as such, 2 units of water diverted because the demand was 2. Then this 10 minus 2 will be equal to 8 units of water that they will be flowing downstream at this point. For T equal 2, let's say that we have 9 units of water coming in, a demand of 2. So it is possible to extract 2 units of water because Q in is greater than the demand. So this will be equal to 7, meaning that 9 units minus 2, it will be that. Now, this type of equations, we can actually put it in here as if Q in is greater or equal than the demand, then select the demand, otherwise it will be Q in. You can write this type of equations and you can see that it's actually doing what we were doing manually. Actually, we can fill the entire column. The same here. In this one, we can just write that equation that Q out will be equal to this Q in minus Q out will be equal to this Q in minus the diversion. What I recommend you is that yep, you can actually see that here the river will be dry. Here we're gonna have some water at the end and so on, okay? What I recommend is that you start doing this exercise, you do it actually by hand. Of course, I'm providing you here some guidelines, but the main point is that you're actually thinking of how water, well, using the mass balance approach, first estimate this diversion, and then the mass balance approach to estimate what is the Q out, how much water can be, will be at the end left at this portion of the ridge, okay? Now, this is, we use this equation, the mass balance equation, but basically we ended up having, well, we didn't have any change of storage. It was only doing a mass balance between the inflows and the outflows. But what about if we do have a change of storage? So in this case, if we have a change of storage, basically, so imagine that we have a river. And in this river, similarly to the previous one, we're actually putting a reservoir in here. We're storing water, okay? So we do have, say, we know what is the water coming in. We know the storage capacity. We have a demand here and a certain flow going out. In this case, what we are trying to estimate is the storage. The storage at this, what will be the storage at the end of a specific period of time. But we will be calculating this interactively. Okay, so let's go back here. In this case, what we're going to do is, this is our balance equation. We know that the change of storage, these two guys here, it is actually this variable, and it will be this variable, okay? We know that the inflows is this water coming in. And we know that the outflows is this water coming out here. Okay? Now, in this case, we are requesting that at least there are 2 units of water coming here. Later, we will be talking a little bit more about water allocation. Don't say, why in the previous exercise he didn't do this. And at this point, I just want you to get familiar with the mass balance. Later, we're going to be talking about allocation policies, okay? For now, what I want you to focus is in how to estimate a mass balance, given that you may have certain variables known and certain that they are unknown. So for a period number 1, what we may have is this initial storage. So let's say for, again, and this is the same, it's a monthly time balance. So at the first month that we're going to do this analysis, our reservoir started at this 500,000 acre feet. So that's the value of our initial storage. So given that we know, let me actually change this guy here. No, actually I'm gonna leave that one. So what you can see is that in this case, we already know so at the end of the month number 1 of January, we already know what was our initial storage when we started January. We proposed it 500,000 acre feet. We know what are the inflows. We have the time series data for this water coming into the reservoir. And we know what are the demands, how much water is requested to be released from the reservoir. So in this case, using the mass balance equation and substituting here, this is how we can estimate this storage at the end of the month, which it will be the initial storage plus this inflow into the reservoir minus the sum of the outflows that we know that they are these two. So this will be, again, so here we start with, let's say, 500 units. here for Q in, we know that, let's say that we, let's say that the Q in at this, what we were saying here is about 10 units of water. Let's say that the demand here is about 2 units of water. And then the water coming out of the, that we want to keep at the end of the river, it's 2 units of water. So if we do this mass balance, what will be the storage at the end of that month? That's what we're trying to calculate here. So it will be, you have 500 at 10 units, but then you will be subtracting 2 units because that's the water that you're releasing. So 510 minus 4, 506. That's how we're estimating this. Now, for the following time step, now this 506 will be our initial storage, the storage in the previous time step. Now we have 506 here. We have 9 units of water coming in. And we have the same 2 units of water requested at the end. So 506 plus 9, 515 minus 4, 511. So it has to be 506 plus this minus the sum of the outflows. That's 511. Okay. And similarly, now this 511, it's going to be the initial storage for the previous one. And I wanted to do this manually so you know that we calculate the first line and then we use the last result of the first line as part of the calculation for the following time step. And then again, you do all the calculation, estimate the storage, and that storage will be used for your following time step. So basically, in this case, again, we can do it here. We have 511 units. We have 12 units coming in. And we may have the same 4 units coming out. So in this case, it will be 13, 523 minus 4 should be, I think, the same, 519. Yeah, this guy here. So we can do this automatically in Excel, which is fine. But the main objective here is that you actually do it. Try to do it this by hand. I understand that Excel will help us out later, but I want you to get familiar with this. This is something that is coming in your exam, okay? Now let me see if I can, just to finish the class, what are the things that we need to, that I want to show you again. Just to summarize, we are using the mass balance. The mass balance is once we define a control volume. In this case, our control volume was estimating the water above the reservoir and below the reservoir. That's our control volume. We use the mass balance usually to estimate one of the unknown variables. In this case, we knew pretty much most of the variables, or we proposed to know some of the variables. The one that we were calculating, it was this storage at the end of the time step. Let's actually take a look at some of these here. So let's actually plot the storage that we have here. And actually, what I'm going to do is well, I'm just going to be putting something like this, okay? Okay. Okay. Okay, so this is the storage. This is how the storage started at 500. And then you can see that then it went 506, has this kind of wiggles in here. Actually, we cannot see all the wiggles in here. So let's actually change this instead. Let's change this to 550. And then this one to 400. So now you can actually see all these variables, okay? Throughout the months, how this was changing. That's what I want you to notice here. Okay, in all these different months, how it was changed. Okay, so now we have it in here. So you can see that there are periods of time that the reservoir storage is increasing. And there are some other periods of time when the reservoir of the storage is decreasing. Why is that? Let's actually take a look at the inflows. And let's say at the sum of the outflows. Okay. So the sum of the demand plus the water going out. Okay. Let me actually also plot these two. No. So I know this graph is quite busy, but let me see if I can add here. No. I want to add the legend here. Here. So let's take a look at this. Notice the inflows. Every time that the inflows are greater than the outflows, the change of storage is positive. Every time that the inflows are lower than, less than the outflows, the change of the storage is negative. The change of storage is negative. So let's go back here. Okay. So when the inflows are greater than the outflows, let me see if I can. Okay. Okay. So again, here we have our inflows. This is our red numbers. Okay. Which are plotted in here. So if the inflows these are our outflows. This is the one that we were just, this is this time series data, okay? When we have the inflows greater than the outflows, our storage increases month by month. When the outflows are greater than the inflows, then the storage will decrease. Look, when we have the same values, the inflows equal to the outflows, then there is no change in storage. The value between the previous and this one is exactly the same. When again the inflows are greater than the outflows, then the storage increases, and vice versa. So that's how you can see, in this case for a reservoir, how the change of, well, the mass balance equation is working on. Okay, so we'll talk about this later. We're going to use this concept quite frequently, but for now, I think that's it. Thanks for being here, and then I'll see you next class. See you.